Michael, we can start.
Thank you very much. Can you hear me and see me, Arvind?
Yes, we can see you.
Okay, so we will try this method where the camera is zooming in automatically on me. I hope it will work. If not, then I can ask the person in charge how to cancel this automatic thing. I don't know how to do this myself, but there are all kinds of buttons here. I can try how to cancel this automatic thing and just do it as we did in the room where we were yesterday. Tomorrow, we will be back also in the room where we were yesterday, so it will be the old method. Okay, so, sorry?
Okay, fine, no problem, please.
Thank you. So we are speaking about the spectral representation of the RFM steady state. I see that it's difficult. I lie down a little lower on the board. I lie down a little lower. Sorry. So, can you hear? We are speaking about the spectral representation of the RFM steady state. And we said that we have the RFM with rates lambda 0 up to lambda n. These are the parameters, the positive parameters of the RFM. And then what we do is we build a matrix, I think I called it A, where we place zeros on the main diagonal. All the lambda i's scaled to the power minus half on the super diagonal, and all the lambda i's scaled to the power minus half on the sub diagonal. And then we take this matrix, we know from Perron-Frobenius theorem that there is an eigenvalue sigma which is positive, and the vector v, sorry, that's too high a bit. We know from Perron-Frobenius that there is a Perron root sigma and a Perron eigenvector v with every entry positive, such that AB is equal to sigma v. And then we made some manipulations on this equation. And after making some manipulations, we came to the conclusion that in the manipulated variables, so we define variables di equal to vi plus 2 lambda I 1/2 sigma vi plus 1. We define such variables that depend on the rates, the Perron eigenvector, and the entries of the Perron root and the Perron eigenvector, and we did some manipulations on this. And after we did these manipulations, we got to the conclusion that these DIs satisfy the same equations as the EIs. First of all, the DIs are all between 0 and 1, and they satisfy the same set of equations like the EIs. And because there is a unique equilibrium point in 0, 1, these DIs are just the EIs. So in other words, we know now that we can express the coordinates of the steady state in this form. And we also know that the steady state production rate is just sigma to the power of -2. So we have all these quantities, and I call this the spectral representation of the RFM steady state. And in the last lecture, we started talking about what are the implications of this spectral representation. And I said that first of all, it allows us to use tools, numerical tools for computing the eigenvalues and eigenvectors of tri-diagonal symmetric matrices to compute the EIs, because we compute for this matrix sigma and V, and then we have all the EIs and we have the steady-state production rate. And that's very useful and can well, I'm sorry, for very large values of, so for very long chains. And these algorithms are also robust numerically, so the errors in the computations will be relatively small. That was one implication. Another implication was that sigma here is actually, because of the special structure of this matrix A, it is the L2 matrix norm of A, and then using using the fact that the matrix norm is always convex, is always a convex function, we concluded that the problem of maximizing R subject to lambda I positive and some constraints on the lambda i's, some constraint on the total budget, we can conclude that this problem is a convex optimization problem, and this has many advantages. And today, I want to speak about another implication of this spectral representation, and this is sensitivity analysis. So let me erase some of the parts here. This I will erase, and this I will erase. Maybe I will just keep the definition of EI somewhere, or not the definition, the expression for EI. I just kept that because we will need it later on, perhaps. Okay, now what do I want to do? I want to talk about sensitivity analysis. And in particular, what I would like to do is I would like to define these quantities. What are these quantities? This tells me if I change lambda I, one of the lambda i's by a little bit, what will be the change in the steady-state production rate? So this is, of course, an interesting question, because maybe I can manipulate the lambda i's first of all, and if I can manipulate the lambda i's and I'm trying to maximize R or to minimize R, this can tell me which lambda I has the largest effect and which lambda I is the smallest effect on R. So I want to know, for example, SI large would mean that a small change in lambda I will cause a large change in R. And on the other hand, a small SI would mean that if I make a small change in lambda I will also get a small change in R. So in some sense, this can also provide me information as to which lambda I is more important and which lambda i's are less important in the context of, say, maximizing or minimizing the steady-state production rate. Now, before we use some formulas, I want to give some intuition on what I expect, what will be. So let me claim that every SI is positive. And I want to explain why this claim makes sense. In such a matrix, when we compute the Perron root, of a non-component-wise non-negative matrix, we know that if the entries of the matrix, any entry of the matrix increases, then sigma also increases. So I think intuitively this is clear. We will write equations soon, but intuitively I think it is obvious that if we increase the entries, the Perron eigenvalue, which is the maximal eigenvalue, or the most dominant eigenvalue, can only increase when we increase the entries. I think this is intuitively clear. We will soon see this from the equations, but now I'm just looking for intuition. So what does this mean? Let's assume that we increase one of the lambda i's, fix some I, and increase lambda I. Then the entry in A actually decreases because we have here lambda I appears here to the power of minus half. It appears in two places to the power of minus half. So when I increase lambda I, the corresponding entries in A decrease. So if the entries in A decrease, I expect the Perron root to decrease. And since R, I raised it, since R is sigma to the minus 2, I expect it to increase. So I hope this chain is more or less clear. I increase lambda I, this means that I decrease the entries of the matrix A. I decrease two entries because they appear there to the power minus half. So A is decreased, so I expect the Perron eigenvalue to decrease. And because R is sigma to the power minus 2, I expect R to increase. So intuitively, I think this is clear. If I take my RFM, and there is some rate here between two sides, and I increase this side, and I increase this rate, then the flow goes more, it's easier for the ribosomes to flow through, and then the steady state is expected to increase. So this was just an intuition from the properties of a non-negative, component-wise non-negative matrix to what happens when we increase lambda I, what happens to R. But now we want to do this more rigorously, of course, and to get explicit expressions for the SIs. Any questions about this intuition before I erase it? Okay, so I erase it and I continue. The round node, okay, so sigma is a simple eigenvalue. Simple means that it appears with multiplicity 1. And in this case, sigma is actually a differentiable function of the lambda i's. It is not only continuous, sigma is not only continuous in the lambda i's, it is also differentiable. And there is a formula, known formulas, and if you like, I can prove this formula for you, that says that if you change A a little bit, so if you change lambda I, a little bit, and you want to know, so I change lambda I in A by a little bit, and I want to know what will be the change in the Perron root. And the answer is given by this formula, which, as I said, if you like, I can even prove, I think. But this is known from linear algebra. Now, I can substitute everything here. Vt I keep. V is this the corresponding eigenvector, yes? V here I keep, and I know what happens when I differentiate A by lambda I. Here and here I get, so what do I get when I differentiate by lambda I? I get minus half So I had, let me write again, I had lambda I to the power minus half. Now I differentiate this with respect to lambda I get minus half lambda I to the power of minus 3/2. This is the derivative of A, and all the other entries are now 0. All the other entries are now 0. This I get also here. And all the other entries are 0 because lambda I, which is the term I'm differentiating with respect to, only appears in these two entries. And then I can multiply by V on the left and on the right, and simplify a bit. And what I get is an explicit expression.
Excuse me, sir.
Sorry?
Sir, please adjust the camera because it is not stable.
It's not stable. Okay. First of all, one option is that I will simply not move. If I don't move, I think the camera doesn't move. Let me try the camera. Let me try. Maybe like this. Thank you for telling me. Oh, yes. If I did that, I think, successfully. Okay. How is this now?
Yes,
now
sir.
it's not moving.
Thank you, sir. Thank you.
Can you see the camera?
Yes, sir.
Excellent. Thank you very much for telling me. Okay. So we differentiated A with respect to lambda I. It's very easy. All the entries become 0, except for the entry that included lambda I to the power minus half, which becomes this. And then when I multiply it by V transpose and V on the left and from the right, which is what required by the formula, and I simplify a bit, this is what I get. So the good news is that this is an explicit expression for what happens to sigma as I change a little bit one of the lambda i's, and I know everything here. After I built this matrix, I computed the Perron root and the corresponding eigenvector. I computed them, say, to get the EIs. And once I did that, I have all the quantities here explicitly. For numerical calculation, I have everything I need, and I have an explicit expression for the derivative. And also, I see immediately now that this is positive. Why? R is positive, it is the steady state production rate. Every entry in V is positive, this is positive. So I see now the intuition that I explained to you, where I increased why when I increase the lambda i's, the sigma can only increase, is valid, but here I get much more. I get not only that this is positive, but actually it's an explicit expression for the derivative. And now I show you a few graphs where we made these calculations explicitly. So now I have a way to make a calculation of d sigma to d lambda I explicitly. And I want to show you a few graphs. This is from a paper called Sensitivity of the Ribosome Flow Model. Let me show you some graphs. So what do? I take an RFM with n equal to 200. And I assume, just for simplicity, that all the internal rates, so I have here, I think, up until lambda 201, and here is lambda 200, and this is site number 1. Now, what do? I assume that all these internal rates are equal to 1. I don't have to do that. This equation is valid for any lambda i's that you give me. This will always be valid. But just for the sake of the example, I assume that all the internal rates are equal. This is a little bit like in tacit. But I play with the values of lambda 0 and lambda 201. And I want to explain, sorry, I see that this ends at 200. So I took here 199. No, it's from lambda 0 to lambda n, sorry. So this is 200 from lambda 0 to lambda 2. This is like this. from lambda 0 to lambda n, this is 199. So I have 200 sides. The first lambda is lambda 0, and the last lambda is lambda n. So I took this situation, and all the internal rates are 1. And now this quantity will depend on the lambda i's, of course, because the vi's and the sigma and the r all depend on the lambda i's. So I need to fix the lambda i's first of all, and then calculate what will happen if I will change one of them. So in the first graph, we took lambda 0 equal to 0.4, and lambda 200 equal to 1. As I told you, all the internal rates are equal to 1. I just play with the initiation rate and with the exit rate. And what I show you is a graph of I between 0 and 200. So this is the index of the rate that I'm changing. This is the index of SI. SI, I'm reminding you, was dr to d lambda I. So I'm showing you a graph of SI, but it's actually a little easier to show lambda SI. SI is a positive number, and I show you the lambda. So it looks like this, something like this, up to here minus 90, and here it's a little less than 0. So the SIs are smaller than 1, they are all smaller than 1, and then the lambda SI are all negative. And let's see what we see in this picture. What we see in this picture is very clear. S0, which is the sensitivity of R with respect to lambda 0, is maximal. S0 is maximal. And this is very natural. Why? Because you see that this is a bottleneck rate. All the rates are 1. All the rates here, the internal rates are 1, and this is also 1. So this is the bottleneck rate. This is what doesn't allow the ribosomes to enter and flow at a relatively high rate. And then the sensitivity to a change in lambda 0 will be maximal. If you change lambda 0, then in some sense you get the maximal effect on maximizing R. Whereas the other rates are less important. If you play with rate 200, it will have a very small effect, because in any case, the bottleneck is here, very far from 200. So this is the rate where you have to invest your energy or your efforts if you want to increase R. And of course, intuitively, this is clear because this is the bottleneck rate. But the good thing is that here we have explicit formulas that give us exactly the value of SI numerically, but an exact value. Now, the second situation, let me erase the explicit equation. The second situation that we want to consider is where lambda 0 and lambda 200 are also 1, so all the rates are 1. So now we are in the situation where all the internal rates are 1, and I also took lambda 0 and lambda 200 as 1. And if I plot the graph of SI, lambda SI as a function of I get a situation like this. This says that the most important rate now is the rate exactly in the middle. Lambda 100, which is the rate exactly in the middle here, is the rate that, if I increase this rate, I will get the maximum effect in R. Now, this is something I encountered several times in the RFM. When all the rates are equal, the most important rates are the ones in the middle. I'm not sure that I know how to give you a good intuition on this. Maybe people familiar with Tasset know this as well, I'm not sure. One explanation perhaps is that the rate in the middle has the largest number of neighbors because it has 100 neighbors to the right and 100 neighbors to the left. So when you increase it, in some sense, you improve the situation in the maximal possible way. But I'm not really sure that I understand the intuition why when all the rates are equal, the middle rates are the most important ones. You know that when you build a bridge, and you want to make sure that the bridge will not develop too many oscillations, the best place to strengthen the bridge is in the middle. Because the oscillations start to develop, they develop along the bridge, and if the middle is secured, then they only have a relatively short distance to progress and resonate and attain more and more energy. So you have to strengthen the middle of the bridge, connect it strongly to something. So here is something similar. Somehow the middle of the RFM, when all the rates are equal, the middle of the RFM is where the critical rates are. And of course, we can also take the situation where, so I erase this. We can also take the case where the dual case, where now lambda 0 is 1, and lambda 200 0.4, and all the other rates are 1, and then I will get something very similar to this, but now in the opposite direction. So now it is the exit rate that is the bottleneck. All the other rates are 1. And because of that, because of that, the SIs, S200, which is dr to d lambda 200, is the largest rate. This is the rate, is the largest, it has the largest sensitivity. So if you want to increase the production rate, steady state production rate, you need to, and you don't know in which lambda to invest your energy, invest it in this lambda, which is the bottom. So this is just a dual situation, of course, of this. Questions about this sensitivity analysis. So as I said, the main advantage is that you have a closed form example, a closed form formula. You have a closed form formula in terms of the spectral properties, which are sigma and V, for the sensitivities of the RFM. Questions, please, if there are any. Okay, if there are questions, please don't hesitate to barge in and ask me. Okay. Okay, now I want to talk a little bit. Okay, so we are done with the spectral approach. My feeling is that there are other things, other implications of the spectral approach that I didn't think of yet. And I think it can be an interesting topic to try and find out more applications of the spectral approach to analyzing the RFM, because I'm sure that this spectral representation has many advantages, and some of them probably we didn't understand it. So now the plan of what we are going to do today and tomorrow, tomorrow is the last day. I want to talk a little bit about the model called ribosome flow model on the ring. Just to say a few words about this, because this is an important model in some sense. This is, in fact, you can take this ribosome flow model on a ring and from the analysis results for this model, you can get all the analysis results for the RFM. And I want to explain what this means. In particular, you can get the spectral representation for the RFM. And after that, so we will spend a little time on this. And the plan for the next talks, I will speak a little bit about something called strongly monotone systems, because this is needed for the last topic, which is networks of RFMs. So this is the plan. We speak about this, and then these two topics, and then we finish. Okay, so what is this ribosome flow model on the ring? It is the mean field approximation of the circular tassel, or closed tassel, which means that I have my sites like in the RFM up to site N, but the flow out of site N doesn't go to some empty reservoir somewhere, but it goes back to site number 1. So as I said, this is just circular tassel, but now in the context of a deterministic continuous time dynamical system. And what will the equations look like? So the flow out of the last site, we have x and dot. The flow out of the last site is minus lambda n xn 1 minus x1 y. It is proportional, first of all, to lambda n, which tells me how easy it is to leave the last site. It is proportional to the density here in this site, site number n. If there are more particles will go to site number 1. And it is proportional to the free space in site number 1, which is 1 minus x1. So if there's more free space in site number 1, more particles can flow here. And on the other hand, when site number 1 starts to fill up, new particles find it more difficult to get. And the flow into site number 1 is exactly the flow that comes from site number n. So in some sense, this model is more elegant than the RFM in the sense that all the equations here look exactly the same. Or if you look at the equations, they are all the same. In the RFM, the equation for the first site and the equation for the last site are a little different from all the other equations. Here, because we have this circular symmetry, all the equations are completely identical. They have the same structure. Now we can compute the Jacobian of this matrix. I will ignore now the diagonal entries because I just want to show you that this is a cooperative dynamical system. So to show you that this is a cooperative dynamical system, I just have to show you that the Jacobian is Metzler for every point in the state space. Of course, the state space is just like in the RFM, the n-dimensional cube, because every density is normalized, so it can only take values in 0, 1. And let's calculate the Jacobian ignoring the diagonal entries, because to show you that it's Metzler, I don't care about the diagonal entries. So here I have lambda 1 x1, 0, 0, 0. And what I have that was added is this term. This term was not in the RFM. In the RFM, we didn't have this term because, okay, so what is this? This is the derivative. I'm differentiating now f1. This is f1 coordinate of the vector field that tells me how x1 changes with respect to all variables. So this is the derivative with respect to x1, I don't care about this. This is the derivative with respect to x2. This is lambda 1 x1. And this is the derivative with respect to xn, which now appears. It did not appear in the RFM. In the RFM, this was 0. But I don't care. All that I care about is that this is always non-negative because x1 takes values in 0, 1, and then 1 minus x1 takes values in 0, 1. So this is positive. And the rest of the RFM is very similar. Here I get also a new entry at this corner. But again, this is always non-negative. So I conclude that this is always Metzler on the state space. And this means that the RFMR is also a cooperative dynamical system, and this means that it is a monotone dynamical system. And we explained, I think, why the RFM is cooperative. I try to give you an intuitive explanation, and also I try to give you an intuitive explanation on what it means that the RFM is monotone. If you start from a day with more traffic everywhere, then this will stay like this all day long. All these properties called here more or less the same. However, there is a big difference between the RFMR and the RFM. And I want to talk now about this difference. The difference is that if I sum up all these derivatives now, look what happens if I sum up all the derivatives. This cancels with this cancels with the next derivative here, all these cancel out, and this cancels with this. So when I sum up all the derivatives in all my differential equations, all my n differential equations, I get 0. What does this mean? This means that this is constant along the flow. The sum of the densities is constant. Of course, this is not surprising. This is because this is a closed system. If you, the particles, no particles enter and no particles exit the system. They just run through the sites and maybe change the configuration. But this is a closed system. Unlike the RFM, where particles enter into site number 1 and can leave site number n, here the total density, so the total density is constant. And what this means is that if you take some initial condition A, so you start here with density A1, and here with density A2, and so on, and all the AIs are of course in 0, 1. Then, when you look at the total density in time t, it is always equal to the total density at the initial condition, because the total density does not change. So as I said, the total number of particles remains the same. They only redistribute between the sites. And this is an important property because when we will speak about networks of RFMs, the network that we will talk about, I don't know yet how much time we will have exactly, but the main network that we will talk about will also have this property that it is a closed system and the total density of particles remains the same. So this is I think in some fields of mathematics or maybe physics, this means that we have a first integral. The dynamics has a first integral. You know, this is like a pendulum, for example. If you look at the pendulum without friction, then if you sum up the potential energy and the kinetic energy, then this is so if you sum up the kinetic energy and the potential energy, these are constant because if there's no friction, there is no addition of energy and no reduction in energy, so the total energy is constant. Some people call this the first integral of the motion. So in this case, the first integral of the motion, if you like to write it explicitly, the first integral of the motion is, I don't know yet what I can erase, let's erase here. The first integral of the motion, maybe we can write it like this, hx sum of xi, this is the first integral of the motion. And this has important consequences on the dynamics. Okay, so let me now say a few words. Okay, so first of all, what does this mean? We are in a class, in an important class of systems, cooperative systems that admit a first integral. And this is a class of systems that have been studied by several authors because, of course, they appear in many fields of physics, economics, systems biology, chemical networks, and more. Whenever you have some conservation, some energy, the number, the total density, something is conserved, and the system is cooperative, then you're looking at a cooperative system with a first. Questions about the RFM so far? This is also a good introduction to the first network of RFMs that we will study. Please, any questions? Don't hesitate to just barge in and ask. Okay. So for any S in 0n, the density, the total density, this is this constant density, of course, is always between 0 and n, because if we start with 0 density in all the sides, then the total on all the densities is 0. And if we start with all the sides completely full, so there is density 1 in each side, then the total density is n. So the total density is always between 0 and n. For any s in 0 and n, let us define the following quantity. This is all the y's, all the vector y's in the unit cube, such that sigma yi is equal to s. We call this the S level set of H. H is our first integral. And I want to look at all the points in my state space where the first integral is exactly S. So for example, let's make an example to make this clearer. For example, assume that n is 2, so we have just two sides with a circular chain, side 1 and side 2. And let's look at what is L1. L1 includes all the configurations where the sum of the densities in the two sides is equal to 1. When I say L1, this means that the sum of all the densities should be 1. So for example, if I take the density 1, 0, 0 here and 1 here, this will be a density in L1. If I take the density 1, 0, this will be a density in L1. If I take the density 1/2, 1/2, this will be a density in L1. I look at all the possible densities in my sides, such that the total density is equal to S. Okay? So it's like considering, because we know that if I start with some total density S, it remains S along the dynamics. So it is natural to consider the system on this S level set. Okay, let's talk about this as if it's an energy. Although it's not an energy, it's a total density, but let's think about this H as the conserved energy. So I want to look at all the configurations in which I have exactly this energy. Let's think of this like that. LS are all the possible configurations where the total energy is equal to this. And now we can prove the following result on the RFMR. For any S, so this is proposition 14 in the lecture notes I will send you. For any S in 0n, the set LS, so again, these are all the configurations where the total energy or the total density is equal to S, includes a unique steady state ES. Okay, I denoted ES because for any LS, I will have a unique equilibrium there. And I want to denote, to make sure from the notation that you understand that this equilibrium point is the one corresponding to LS. So I denote it by ES. And any solution of the RFMR with any solution, okay, let me write it a little different here, sorry, where was that? Okay, and for any initial condition, A on LS, we have, what we have, it's the A goes to this. So we fix an initial condition on this manifold LS, and then for any such initial condition, it will converge to this unique steady state on LS, which we call ES. So let me make a schematic graph of what this means, or some intuitive explanation. Again, let's take just two sides for simplicity. Of course, all the results all for any dimension. This one's for any dimension. And let's take L1. So this means I can take as an initial configuration, I can take as an initial configuration this one, or I can take this one, or I can take this one, or I can take this one. All these initial configurations correspond to the situation where the total initial density is 1, and from all these initial configurations, I will converge to some unique equilibrium called E1. When I look at all the initial configurations that belong to L1, and I simulate them and consider what happens, they will all converge to an equilibrium that I denote by E1. And now if I take different initial configurations, for example, if I take initial configurations where the sum is 1/2, so this one, this one, this one, they will also all converge, the solutions will also converge to a unique equilibrium, but now a different equilibrium, not necessarily E1, this is E1/2. So the proof of this result is from known results on the behavior of cooperative dynamical systems that admit the first integral. So this is proposition number 14 in the lecture notes that I will send you. And this tells me basically that for any initial condition, I will converge to an equilibrium. In particular, why? take some initial condition, it belongs to some LS, any initial condition that you give me, you just sum up the total density in A, you get the sum, and the sum, and then you belong to some LS, and from this configuration and from any other configuration in LS, you will converge to this unique equilibrium in LS, which we denoted by ES. And now let's try to see, again, I would like to say something about the equilibrium. And actually we can get, just like we got for the RFM, we can get a spectral representation for this steady state, but here we need to be a little bit more careful. So let's try to see what the equilibrium point looks like. So for simplicity, let's take an RFM with n equal to 3, just to see on a concrete example what the equilibrium point equations look like. Let's take an example. It's always easier for me to look at a specific example than to consider the n-dimensional general case. So I took an RFMR, Iverson flow model on a ring, with three equations, with 3 sides. And now at the equilibrium, what happens? I put here E3, I put here E1, I put here E1, I put here E2, and I get 0 in the derivatives. So this gives me like this, E3, lambda 3 E3, 1 minus E1 is equal to lambda 1 E1, 1 minus E2, and this is equal to lambda 2 E2, 1 minus E3. These are the equations I get from substituting E instead of X and equating the coefficient, the derivatives to 0. And here there is an interesting phenomena. E will include three coordinates, but here I just have 2 equations. These are just 2 equations. Yes? This is equal to this, this is equal to this. These are just 2 equations. So there's not enough information to deduce E explicitly. But I also know one more thing. If I started from initial condition A, then I know that sigma AI is equal to sigma EI. Why? Because of the conservation of energy. This is, or conservation of density. This is the density at the initial condition. And this is the density after infinite time when I converge to the steady state. And of course, I know that the density is constant. The density, the total density cannot change. So this gives me the third equation, another equation. And once I know the initial condition, so for any initial condition, I take these 3 equations and I get 3 equations for 3 unknowns, and then I solve this and I get the steady state. And of course, if I will take a different initial condition, but in the same level set, so imagine that sigma AI, just as an example, is 1/2. If I take a different initial condition, but again with the same density, so sigma AI theta 1/2, then of course I will converge to the same equilibrium. Why? These equations remain the same. And this equation also remains the same because it only depends on the total density at the initial condition. So if you keep the total density the same, you will get the same set of equations, and then you will get the same E. This is exactly what this theorem says, or this proposition says. If you stay on your set LS, you take different initial conditions, but all in your set LS, so all of them with an equal total density, you will converge to the same equilibrium that we denote by this. Questions about this? Yes, please.
Any question from the audience side?
Okay,
question.
Let me just say one thing here, just one notation that I forgot to introduce. After I converge to the steady state, after I converge to the steady state ES, the flow is any one of these equations. So for example, I can take lambda n minus 1, En minus 1 S multiplied by 1 ENS. So this is the steady state production rate or the steady state flow after I converge to the equilibrium point S. These are all the flows and they are all equal. So I can take, for example, this one, lambda n minus 1, En minus 1, 1 minus En. And remember, I denote En by ENS because for every level set Ls of my first integral, I have a different equilibrium point. Okay, so in the next talk, we will talk a little bit more about the RFMR. There is an interesting spectral representation here for the optimal steady-state flow. I will speak about this. And then we will see that from this spectral representation, we can actually get the spectral representation of the RFM. But in some sense, things here are completely different because you have to take into account this equation as well. If you don't take into account this equation, you don't have enough equations to specify uniquely your equilibrium point or to solve your equilibrium point. So in some sense, this is very different from the RFM. We have here this conserved quantity that we don't have in the RFM. But on the other hand, we will see that from a specific case of this RFMR, we can actually derive all the results on the RFM. So I don't know if this is the same in TASEP, if from considering the circular TASEP or the closed TASEP, by taking some limit, you can get the linear TASEP. But we will see that here it is possible. From the RFMR, you can get, when you take some limit, the RFM. Okay, so I think I will let you have 3 more minutes. I don't want to start anything new now, only answer questions if you have. And then we meet again, and where is my schedule? We meet again in 2 hours.
Any question from the audience? Okay, I think there's no question, so maybe we can close this session and we'll meet at 3 o'clock.
Thank you very much, Arvind. Thank you.
Thanks.
See you in 2 hours.